7A. And you go, where do you find the group number? When you're looking at a periodic table, the vertical columns are called groups. All right, so look up at the top and it says group 17. If you look down, bromine has an atomic number of 35. The atomic number again represents the number of protons in the nucleus. And the nucleus was discovered by Ernst Rutherford back in the 19-teens. It's where the protons and neutrons are located. There's a little history lesson. The first subatomic particle was the electron by J.J. Thomson. He discovered the charge to mass ratio. He knew it was negative, but he didn't know the actual charge of the electron. Millikan in the 1900s determines the actual charge of the electron and the actual mass of the electron. And then in the 19-teens, Rutherford, while firing alpha particles at a piece of gold foil that was so thin that light can pass through it, noticed that some of the alpha particles were reflected backwards. And he said, well, there must be something massive in an atom that can knock an alpha particle backwards. Kind of like throwing a baseball. When it hits a wall, it bounces back at you. Well, that's what was happening to the alpha particles. So Rutherford's given credit for the discovery of the proton. It's not really until the 1920s or 30s they say that the discovery of the neutron occurred by a guy named Chadwick. So anyway, what we want to do here is we want to be able to classify where the electrons are for a bromine atom here. So we know there's 35 protons by the atomic number, and for this atom to be neutral there has to be 35 electrons. So where are they? Well, the group number is one place to start. Whatever is in the ones place of the group numbers, this is the modern way of doing it, group 17, whatever's in the ones place, that tells you how many electrons is in the outer shell, or the valence shell. So bromine has 7 valence electrons. That means there's 7 electrons in the outer shell. The old naming system or group numbering system, the 7 would tell you how many electrons is in the outer shell. So we're going to use the new system for the most part. I do want you to know the old system as well, but the new system, the advantage of it, it's continuously numbered across 1 through 18. And if you just remember that groups 1, 2, and 13 through 18, whatever number's in the ones place represents the number of valence electrons. That's going to help you tremendously. In fact, groups 1, 2, and 13 through 18 are called the representative elements. And when that phrase or that name was first used, it was believed that if you had an element out of each one of these groups, you could represent any chemical or physical property in the universe. We know that's not true today, but we still call them representative elements, and it helps us indicate which elements can we look at the group numbers and determine the number of electrons in the outer shell. So, how many shells are around the nucleus? Well, let's talk about what a shell is first. I think a lot of people get... If we go back to the 1920s, there was a guy by the name of Bohr who he believed that the electrons orbited the nucleus much like the planets orbit the sun, that there was an exact path that the electrons followed around the nucleus. In the late 1920s, 1930s, there was a new theory about how electrons behave called quantum theory. In quantum theory, when we look at mathematical equations to describe the behavior of an electron, the electron does, we cannot know the position and speed or momentum of the electron in relation to the nucleus. So the best we can do is where's a 90% probability of finding the electron? Where is the 90% probability? Well, that's why these are called shells. Instead of the electron being right here on this shell, or in an orbit, we're saying the electron is in here 90% of the time. And we're okay with that. And so to make this a little more clarified, we don't draw all that. We just put a little half circle like that and say the electron is in that shell 90% of the time. So the shells, how many shells does bromine have? Well, the indicator for that, without getting into the quantum mechanic calculations, is to look where bromine is located on the periodic table. It's in group 17. We know it has 7 valence electrons. And so the groups are the vertical columns. Well, the horizontal rows are called periods. And so bromine is in period 4. It's in the 4th period. So that tells us that we should have 4 shells around the nucleus of bromine. So, how many electrons is in each shell? Well, the maximum number of electrons that can be held in any particular shell is this mathematical calculation, 2n squared, where n represents the shell. So the first shell, n equals 1, we get 2 times 1 squared, and that's 2. N equals 2, we get 2 times 2 squared, that's 8. N equals 3, we get 2 times 3 squared, and that's 18. And n equals 4, we get 2 times 4 squared, which is equal to 32. Now that's the maximum number of electrons that can be held by any shell. We know that in the fourth shell, the outer shell, there's only 7 valence electrons. So we know that. How do we know that? Again, the group number tells you how many electrons in the outer shell. Why is that so important? It's because the outer shell electrons are those are the electrons that are going to be involved in any chemical bonding. All right, so we need to figure out how many electrons in the other 3 shells. Well, the first one is 2. And you could see that, 2n squared. The second one is 8. And the third one, we can have a maximum number of 18. So if we put 18 in here, we would have 2 plus 8 plus 18, 28, plus 7, 35. Oh, there's my 35 electrons that go with the 35 protons that we said for the group number up here. Now, will they always be maximized out? No, because in the fourth shell we can hold a maximum of 32, but we only have 7. So let's talk about how we know how many electrons go in each shell. Well, you're going to use the periodic table to do this. You look at the first period on the periodic table. There are 2 elements, hydrogen and helium. Helium has 2 protons. The first 2 electrons go in the first shell. So there they are. We drop down to the next element, lithium. Lithium starts the second period. That tells us we need to start the second shell. And if we count across lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, there's a total of 8 elements there, and we've added 8 more electrons. So that's how we get this 8 here. All right. Once we get to neon, we drop down to the next element, which is sodium, which starts the third period. All right. Now watch what happens here. When we count from sodium over to argon, again we go sodium, magnesium, groups 1, group 2. Then we jump all the way across the periodic table to group 13 and go aluminum, silicon, phosphorus, sulfur, chlorine, argon. That's a total of 8 electrons at that point in shell number 3. All right, so there's 8 of them. Now, from argon, we drop down to period 4. That starts the 4th shell. We go potassium and calcium. So there's 2 of the 7. Now watch what happens here at calcium. In the previous periods, we've been jumping from group 2 to group 13. But now we have a bridge between group 2 and group 13. And that starts groups 3 through 12. These are called the transition elements or the transition metals. And that's what a bridge is, right? It's a transition from one landmass to another. So that's what's happening here. These elements are acting as a bridge. Scandium through zinc, number 21 through 30, are acting as a bridge between the first 2 groups and the last 6 groups. Well, something weird's going on here. We have to go back to the 3rd period and we start adding electrons here. We add 1 for scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. Well, that's a total of 10. So there's where our 18 comes into play. We didn't have it initially. Initially, we only had 8 when we finished the 3rd period. But after going through the first transition metals in period 4, we go back to the 3rd period to add those transition metals, electrons. And then we pop out on the other side at gallium. Right now we only have 2 in the outer shell. But now we're going to go gallium, germanium, arsenic, selenium, bromine. We're going to add 5 more. And 2 plus 5 gives us 7. So you're going to use the periodic table to help you build how many electrons is in each shell of the atom. And in the next lecture, what I'll talk about is actually classifying where these electrons are. Are they in an S suborbital or a p orbital or a d orbital? I hope this helps, and we'll continue on